In the last video, I discussed the heat of reaction, and I did a practice problem in which the heat of reaction was given. Most times, these heats of reactions can be measured with a direct experiment. However, some reactions, undesired reactions, for example, that are recurring in parallel with a desired reaction cannot be performed in isolation. And therefore, when you're performing an experiment and you want to know what the heat of reaction for the undesired reaction is, it can be nearly impossible to separate that from only the desired reaction. So in this case, when you cannot accurately measure an experimental heat of reaction, you have to invoke Hess's law as a way to calculate it. Hess's law simply says that if you can derive a chemical reaction by algebraic manipulation of other chemical reactions, you can calculate the heat of reaction by performing the same series of algebraic steps on those heats of reactions, which you have to know. This Hess's law takes advantage of the fact that enthalpy is a state function, which I've said multiple times before, and reflects the fact that just by combining chemical reactions, you can calculate what the heat of reaction ought to be. Hess's law is, I think, something that is best seen with an example, so I'm going to do an example problem now. Let's try this problem. Use Hess's law to calculate the standard heat of the water-gas shift reaction, where carbon monoxide and water vapor react to form carbon dioxide and hydrogen gas. And I have two separate avenues for which I can calculate this reaction. These are kind of simplistic examples, but if I label, let's just do part A first. I've labeled the first reaction A1 and the second reaction A2. And if I notice that if I take reaction A1 minus reaction A2, I will obtain carbon monoxide in the gas phase plus H2O liquid minus H2O liquid, which will cancel out algebraically, goes to CO2 plus H2 minus H2O vapor. And really with algebraic manipulation of chemical reactions, it gets kind of weird. Like you wouldn't necessarily say minus H2O, but if I subtract H2O, that's the same thing as adding H2O gas to both sides. Vapor, sorry, not gas. All right, so by subtracting A1 minus A2, I obtain the reaction that I want, and therefore I can take the heat of reaction 1 minus the heat of reaction 2. So 1226 BTU minus 18,935 BTU is equal to minus 17,700 BTU. You can do the same thing with part B, where I say if this is B1 and this is B2, then I'm going to have to subtract these again. So if I subtract the two equations now, my 1/2 O2 is going to cancel out. And I'm going to have a minus H2 on the left side and a minus H2O on the right-hand side. If I just switch those two or subtract them, like I said, I can get the reaction that I want. So B1 minus B2 is going to yield CO gas plus H2O vapor going to CO2 gas plus H2 gas. So again, here I have to take heat of reaction 1 minus 121,740 minus negative 104,040, which is also minus 17,700 BTU. All right, let's do another example. Let's do a simplified, more generic example. So let's say I want to know what the heat of reaction for this chemical reaction is. So B plus 6E going to 2D. What is delta HR, the standard heat of reaction? And as given data, I have the following. So given that 2A plus B goes to 2C, and A plus D goes to C plus 3E. And I have heats of reaction here. Let's call this one 1. Let's say this is minus 1,000 kilojoules. And the heat of this reaction 2, standard heat of this reaction 2 is minus 2,000 kilojoules. So how can I go about algebraically manipulating these two equations to get me the result of my first equation? This one's a little bit more involved, but you'll see if I take the first reaction and then subtract 2 times the second reaction, so 1 minus 2 times reaction 2, what is that going to get me? So first, let's multiply the second reaction times 2. 2a plus 2d goes to 2c plus 6e. And then I'm going to subtract that from equation 1. So 2a plus b goes to 2c. And you see that when I subtract them, the 2a's are going to cancel and the 2c's are going to cancel. And I'll be left with b plus 6e goes to 2d, exactly what I want. Where once again, I have the negative 2d on the left-hand side and a negative 6e on the right-hand side that I just move over to the other side. So here, once again, I'm going to figure out what the heat of reaction is by doing algebraic manipulation in the same manner as I did on the chemical reactions. So it's going to be the heat of reaction 1, which is minus 1,000, minus 2 times the heat of reaction 2. 2 times negative 2,000 is negative 4,000. Negative and negative is a plus, and this is going to net me 3,000 kilojoules as my heat of reaction. So this is Hess's law. There's some more examples that I recommend in the textbook if you're interested in going into more detail on this, but that will complete this video, and I'll see you in the next video.